Alright, in this video, we consider the problem of constructing the set of complex numbers, given that we already know well enough about real numbers. Okay, let's start. So the motivation for constructing the set of complex numbers is to solve the quadratic equation for any real coefficients. So we have this equation where a, b, c are real and a is non-zero. And we have seen that this equation has real solutions only when b squared minus 4ac is non-negative. Otherwise, we have to deal with the square root of negative numbers, which is undefined. To solve that problem, we formally introduced the square root of 1 and named it as the imaginary unit. However, what this means is not so clear, so what can we do about it? That's the motivation for rigorously constructing the set of complex numbers. So, our approach is to start from the set of pairs of real numbers. Okay, so A and B are reals. Of course, this R squared is the Cartesian product between real numbers and real numbers. Okay, so this is just a set, and that's it, nothing more. So there's not much we can do about it, but now we introduce some arithmetic operations on this set. Okay, first is addition. So we define addition between two pairs of real numbers. Let's say AB and CD as element-wise addition. A plus C and B plus D. Okay, be careful. Here, this plus is now being defined. Okay, to begin with, we didn't have any addition between pairs of real numbers, so we are now defining what this means by this right-hand side. On the right-hand side, we have two additions, A plus C and B plus D, but they are just addition between real numbers. So A and C are just real numbers. So A plus C is just an addition between real numbers, and which we already know. Okay, so by this we define this addition. Now let's see some of the properties of this addition. To begin with, we can see that this addition is commutative. That means AB plus CD is equal to CD plus AB. So we can swap the order of addition. And this can be proved very easily. So by the definition of addition, the left-hand side is equal to this. So A plus C and B plus D. But this addition is just the addition between real numbers, which is commutative. So this is C plus A, and similarly this is D plus B. But this is the definition of the addition between C, D, and A, B. Therefore, which is the right-hand side. Therefore, the addition here is commutative. And next, this addition is associative. That means if we have three pairs, then this addition, this sum, A, B, C, D, and E, F. So first we add C, D, and E, F. Then to that we add A, B. This is equal to this A, B plus C, D first. Then to that we add EF. Okay, so this outer parenthesis can be swapped, moved to different places. And because of this, we can write this summation as simply as AB plus CD plus EF without extra parentheses. Okay, so this is associativity. And proving this is an exercise. You should try that. And next, there is a special element that is 0, 0. And this acts as the additive identity, which is often called zero element. Okay, so it's not just zero of the real number, but it's a pair of two zeros. Okay, what this means is that for any element AB, if we add 0, 0, we get the original element unchanged. So this is the property of that defines the additive identity. And next is the existence of additive inverse. That is, for any element AB, if we add another element that is minus A and minus B, then we get 0, 0, the additive identity. So for any element, such an additive inverse exists. So this is yet another important property of addition. And next, we define multiplication between two pairs of real numbers. So if we have AB and CD, we denote multiplication by this symbol, star. Okay, this is not defined as element-wise multiplication, but instead we define it as AC minus BD and AD plus BC. Okay, this may look strange, but as we'll see, this works out fine. Let's see some of the properties of this multiplication. And first of all, it is commutative again. So AB star CD is equal to CD star and AB. Okay, to see this, just apply the definition here. So the left-hand side is, by definition, AC minus BD and AD plus BC. But of course, this is just multiplication and subtraction of real numbers. So multiplication in real number is commutative. So AC is CA and BD is DB, DB, and AD is DA, and BC is CB. But this is the definition of multiplication between CD and AB, which is the right-hand side. Therefore, it is commutative. And next, again, we see that this multiplication is associative, just like addition. Okay, so that means AB times CD times EF. So we first multiply these two elements, then multiply AB. This is equal to, we first multiply AB and CD, then multiply EF. So we have the same result either way. So because of this, we can just write, instead of putting extra parentheses, we can just write like this without additional parentheses. And proving this is also straightforward, although it's quite cumbersome, but you should try that. So associative, multiplication is associative, just like addition. And next, there is a special element that is 1, 0, which acts as the multiplicative identity. So what is it? It means if we multiply any element, say AB, by this element, 1, 0, then we get the element AB unchanged. So this is the property that defines the multiplicative identity. So this element acts like 1 in real numbers, right? So in real numbers, for any real number, let's say A, if we multiply by 1, we still get A. So A is unchanged by the multiplication by 1. So in the case of pairs of real numbers, this element, 1, 0, acts like that. Next property is the existence of multiplicative inverse for non-zero element. Inverse. So if AB is not the zero element, of course, this zero element is the additive identity element, right? So if this is the case, that means either A or B is non-zero. If this is the case, then there is some element. So if for any element AB that is non-zero, there exists some element CD such that AB times CD is equal to 1, 0. So the result is the multiplicative identity. And actually this CD is, such CD is given by this. That is A over A squared plus B squared and negative B over A squared plus B squared. Okay, so for each non-zero pair AB, this element, this pair is the multiplicative inverse. Okay, let's check that. So AB times this element. So just apply the definition. So A, this times this is A squared and A squared plus B squared and minus this. So we have minus sign here, so that becomes plus B squared. Okay, so they are cancelled and becomes 1. And the second element, A times this one, is negative AB. And B times this one is positive AB. So they are cancelled, so it becomes 0. So the result is 1, 0. Indeed, the result is the multiplicative identity. Of course, it has to be right, a non-zero element, right? So what if both A and B are 0? Then you see here, we have A squared minus plus B squared in the denominator. So that will be division by 0, which is nonsense. So it's undefined. But as long as this is true, AB is non-zero, then we do have inverse. Okay, so that's enough for the properties, but notice that we didn't define subtraction like AB minus CD, or division like AB divided by CD. We didn't define this, but there's no problem with that, because if we just use the convention that negative, what do we mean by negative CD? is it's just the addition of the additive inverse of CD. Okay, so this is just another way of expressing A, B plus negative C and negative D. So subtraction is defined in this way. And this one, division. Of course, we're assuming that CD is non-zero. So this can be defined as just multiplication between AB and the multiplicative inverse of CD. That is C of C plus C squared plus D squared and minus D, C squared plus D squared. So in essence, we can do all the arithmetic operations, addition, subtraction, multiplication, and division by non-zero element. So this set, together with addition and multiplication, acts like any other set of numbers, like real numbers or rational numbers. Okay. For integers, we cannot do division like this, but for rational numbers and real numbers, we can do addition, subtraction, multiplication, and division, just like this. So such set, equipped with addition and multiplication, are called fields. Okay, and in another video, we will summarize the axioms of fields. Okay, that's enough for this video. Next, we consider a map from real numbers to pairs of real numbers. Okay, let's call that map theta. And that is defined by, so for each real number, theta of r is defined as r0. Okay. Note that this map is injective. That means if we have two real numbers and that are different, then theta r is not theta of r and theta of s, they are also different, because theta r is r0 and theta of s is s0. Since r and s are different, these pairs are different. Okay, so this is injective. And then consider a set, let's write like this, R with wavy line, as the set of all pairs with the first element being real and the second element being 0. Okay, this is obviously a subset of R squared. And each element of this set, we write like if A belongs to, wait a minute, if A0 belongs to R, then we write this as A with wavy line. Okay. On print, we write this with boldface. Okay. This also boldface R and boldface A. So, and you can see that all elements of this subset behave just like real numbers. For example, if we have 2 plus 3, then that is 2, 0 plus 3, 0. And that is 5, 0. But this is 5 wavy line. So 2 plus 3 is 5, right? So just like real numbers. And multiplication also. Let's see, 2 times 3. This is defined as this, 2, 0, star, and 3, 0. So that is 2, 3 minus 0, 0. And so that's 6. And 2, 0 plus 0, 3, that's 0. So again, this is 6. So 2 times 3 is 6, just like real numbers. By the way, what's interesting is, what about 1/2 wave number. So a waveline that is 1/2 0. And if we multiply 2 with 1/2, then that is 2 0 star 1/2 0, and that becomes 1 0. So it looks like 1/2 is also multiplicative inverse of 2, obviously. And according to our definition of multiplicative, our definition of multiplicative inverse, then for 2 0, then its inverse is given as 2 over 2 squared plus 0 squared, then minus 0, 2 squared plus 0 squared, which is actually 1 over 2 and 0, which is this. So indeed, this is the multiplicative inverse of 2. Now let's define a special element I wavy line by 0, 1. And note that this is not in our wavy line. Okay? And if we multiply I with I, then 0, 1 star 0, 1. And that is, according to our definition, that is negative 1 and 0. So that belongs to R, wavy line. So you can see that this I, this special element I, behaves somewhat like the imaginary unit, right? And indeed, it will be considered as the imaginary unit. And also, if we multiply I with any B, where B is in R, okay, then 0, 1 star B 0, and that result will be let's see, B 0 times B and minus 1 times 0, so that's 0, and 0 times 0 plus 1 times B is B. So any element of this form, the first being 0 and the second being possibly non-zero, can be expressed as a product between I and an element of R. Okay. By the way, so the element of R behaves like real numbers, so we can call it real. We can identify it with real numbers. Okay. So any element AB is the sum of A0 and 0B, where 0B can be expressed in this way. So A0 is A wavy line, and I wavy line times B wavy line. And A, B belongs to R. So now you're beginning to see that we are actually defining complex numbers in this way. So indeed, we define the complex number, set of complex numbers, is defined as R squared. So the set of pairs of real numbers equipped with addition and star multiplication. Okay, is this. So complex number is not just defined as a set, but it also comes with addition and multiplication. So how it behaves defines what it is. Okay, this is an important point of view in algebra. So now we call, so every complex number as we defined it is written in this way. So we call this real part, and this part imaginary part. Okay, and this is the imaginary unit. So just for the convenience sake, always writing with this wavy line or boldface is cumbersome. So we just identify this set as real numbers, okay? Because there's a bijection between these two sets. Okay, there's one-to-one and onto correspondence, so they can be just the same thing, considered as the same thing. Okay, and we just write this as just A. Okay, so instead of writing like this, we just write 2 or B or whatever. And of course, originally this set is not exactly identical to real numbers, because this is the set of pairs of real numbers where the second second component is 0. But so in that sense, originally the set of real numbers is not a subset of complex numbers, because this is a set of pairs, this is not pairs. But because of this identification, we regard real numbers as a subset of complex numbers. Okay. Finally, let's summarize all the algebra we have just set up in terms of this notation, A plus IB. Okay, this really means A, B. And A plus IB plus C plus ID really means AB plus CD, right? So just do ordinary arithmetic with this expression. So this is A plus C, and if we factorize I, then we have B plus D times I, right? But according to our definition of addition, this is equal to A plus C and B plus D. So the real part is A plus C, and the imaginary part is B plus D. So it's consistent. What about multiplication? A plus IB times C plus ID. What we really means is here A, B, star, and C, D. So, and by definition, this is A, C minus B, D, and A, D plus B, C, right? So here on the left-hand side, let's just do ordinary arithmetic by using the distributive law. So A times C, and A times ID, so I, A, D, and B, IB times C, so IBC, and IB times ID, so that's I squared BD. Okay, but we know that I squared, okay, I squared, I squared is 0, 1, star 0, 1, and which is negative 1, 0. So we can replace, whenever we have I squared, we can replace that with negative 1. Okay, so this becomes AC, so this one becomes negative BD, and factorize I here, we have AD plus BC. So the real part is AC minus BD, and the imaginary part is AD plus BC. So it's consistent. So this seemingly complicated algebra is just the algebra of complex numbers as we know it. So we are done. So this is what complex numbers are. Okay, so we're done, and for this video and see you later.